Hello everyone, my name is Daniel and I'm a programmer and an artist, and today I was experimenting with making this procedural sort of wood texture, which uses a wave texture in the rings mode to create sort of a 3D texture of wood grain, which you can then map onto any shaped object using the position coordinates. However, it only works if the object is aligned to the axis. So as soon as you rotated this some other way, then the grain still runs straight up and down, and then it looks really weird on the board. And so I was trying to think of a way to solve that without having to have all of the objects. Otherwise, you have to build your whole structure or whatever using individual objects and keeping everything aligned, and your boards would have to be perfectly straight. So I was trying to come up with a way to have calculate those coordinates on a whole mesh, which I did. And in the process of doing that, I ended up making this node group that allows you to take a mesh that has sort of a volume to it and then create a curve running through kind of the center of that volume. So it takes this mesh and turns it into these curves. And then I was using those curves to generate those texture coordinates, but I thought you could actually use that for probably other things as well. It just sort of seems useful to be able to take a mesh volume and turn it into a curve. So I thought I'd go through that node group and show how it works, how I'm doing that. So this is the node group here. It looks like a lot, but it's actually can sort of be simply thought of in 3 distinct steps. The first step is to create a bunch of edges to determine the direction that the plank is facing, and then we're going to filter those edges down to a single simplified edge. So you can see this here, that's the straight edge. Here we've simplified it to a single edge, and then we're going to compare that edge to the original mesh and shape it to sort of fit the curve. So you can see this is just a single edge. It has 2 points, one on either end. It's perfectly straight, and then over here at the end we have sort of a curved plank because this one's slightly curved, or you can see this one here, it gets that zigzag sort of shape in it. So those are the 3 steps of what we're doing here. To go through it in a little more detail, for this first one here, we're looping through each element in the mesh, which each instance would be a single plank if you had more than one in here. So if we made a copy of this, we'd have 2. And then we're going to create a bunch of random edges between random points in the mesh, and we can control how many of those there are. Seemed like as few as 32 could work well, but I initially had it set at 100. And then once we have those random edges, we're going to filter out some of them. So we're going to delete any that are too short, and then we're going to sort of average the rest of them together to get this single edge with 2 points. And then we're going to take the input mesh, the 3D geometry, and put a bunch of points on the surface so that it's high enough resolution that we can sort of sample against those points. And once we have those points, then we're going to resample the curve. So we're going to start adding points to the curve, and then we're going to move those points in the curve to the average position of chunks of the surface. So all of these surface points here are used to derive the position or influence the position of this endpoint here, and these ones in the middle to this one, and so on. And then as you go, you add more, and you keep refining and making it more and more precisely fit the shape. And so then in the end, what you get is this curve here. Then we can just extend it a bit if we want to make sure that it reaches the end. So those are the steps that I was doing to get this curve that fits inside the sort of the volume of a surface mesh. And what we're using to do that primarily is splitting the mesh islands into instances and assigning them group IDs. And then we're doing a bunch of accumulating of fields and stuff and sampling where we use that group ID to limit what that node's able to look at, which is a bit annoying and kind of confusing every time you do it, just because you need to have this plank ID integer grouping that goes through to all of these nodes, but hopefully I'll be able to explain it clearly. So Looking in detail at the very first step here, what we're doing is we're taking our input mesh and we're going to create a bunch of random edges between them. So the first thing to do is to take our single mesh and split it into parts using split to instances. And for our group ID for that, we want the island index. So this island index is actually ends up being the same as our Planck index that we use everywhere else. That's this green thing that chains all the way along to all of these nodes. To create the actual edges between the points in the mesh, for each element in the mesh, we're going to realize it and turn it into an actual mesh again, because it comes in as an instance. And we need to know how many points are in that mesh, and then we're going to pick a random point. So we need a random index between 0 and 1 less than the number of points in that one Planck of the mesh. And then we're just going to sample the position of that one index. And I have here a mesh line that has 100 edges in it. And we're going to set up a vertex in that mesh line to a random position. And the input mesh, and what you get is this result here where you get these random edges. Why do we do that? Well, the reason we do that is because we can't guarantee the topology of the input mesh. It might be high resolution and curved like this one, or it might be just a simple quad like this one. And we want to be able to work on both of those, but a solution like just looking at the longest edges would work on this simple cube, but the longest edges on this one are actually these ones that go around the Planck, so that wouldn't work on this mesh. So as a way around that, what I decided would work well would be to connect a bunch of random points in the mesh, which as long as it's roughly convex, if it's not too concave like a torus or something, then that should give us a good approximation of lines running through the volume of the mesh. So you can see that's what we get here. It can be a little bit off. We can have some curves in there, but a really big curve, like a C shape or something, probably won't work. But for something like wood grain, that wouldn't work as well either. Anyway, once we have these random edges, you can see there's some of them here, like these ones at the end, that we don't really want. And so an easy way to filter out some of those that might be sort of random is just to delete any of the ones that are shorter in length than the average length. So the way we can do that is we can calculate the length of all of the edges. Here, if we get a viewer node, we can see here we have the lengths of all of the different edges. And we do that by taking the position 1 and position 2 of the edge vertices and plugging those into a distance vector math node. Then we can calculate the average of that using accumulate field. We want to accumulate on each Planck separately. So we plug our Planck ID into the group ID of our accumulate fields. We want to accumulate one that is the sum of all of the edge lengths, and we want one that just counts how many total elements we have. So in this case, we should have 100 edges, or 99, and we divide our total length of all of those edges by that to get the average. Then if the length of an individual edge is less than that average length, we're going to delete it. So that's what we have here. You can see we go from this, we delete all of those shorter ones there. Then I split the edges with a split edges node, just so that, because it was a mesh line, they were all connected together. And so by splitting them, I make sure they're all separate edges that aren't connected together. Then we have these different edges here. If we look at some arrows, you can see here we have all of these edges, and I put these arrows on them to show the direction that they are pointing. So the way we get the direction is we take those edge vertices again and subtract them. And then if we normalize that, we have a unit length vector that points in the direction of the edge from vertex 0 to vertex 1 of the edge. And then if we look at these arrows and we scale them, we can see that for each Planck, some of the arrows point in one direction and some of them point in the opposite direction, approximately. And I want to flip half of those around so that all of the arrows on a given Planck point in the same direction. And so that's what I'm going to do next. I'm going to separate these into two halves where we have all of the, for any given plank, all of the arrows pointing one way in one group and all of the arrows pointing the other way in the other group. And that way I can flip half of them around to point in the same direction. So the way we can determine if two things are pointing in the same direction is by doing a dot product on two normalized direction vectors. And the two direction vectors I want to use are the direction of a given edge, each edge in the mesh, and then the direction of an edge we're going to compare to, which we could just look at the first edge in a plank, in a group. So how do we get the direction of the first edge in a group, and so we can compare all of the edges against that? Well, one way we could do that is by potentially sampling at the index of that edge, but we need to know what the index is. The other way, which is what I opted for here, was to use some tricks with accumulate field to isolate the direction of that first edge. So the way you can do that is by using an accumulate field where you just accumulate a value of 1. Then the trailing value will equal 0 only on the first edge in a group. So if we view this value here on these edges, we'll see that for each given plank, it starts at 0 and counts up to however many edges there are in that group from that plank. And if we say, does that trailing value equal 0, we'll get all zeros except for 1 on the first edge on the different planks. So you can see those ones there. So what we can do, so now we have like a selection of the first edge, and what we can do is we can scale our direction vector that we have by that selection so that all of the other edges, directions, become 0 except for the first edge, which is the one we care about. And then if we use another accumulate field and look at the total, we get only that one edge we selected on all of the edges. So if we plug this into our arrows here, we can see now all of these arrows point in the same direction, but they don't align to the edge anymore. You can see this edge here goes off at an angle, but they're all pointing in a different direction. But then we can compare the actual direction of that edge to our the one we're testing against, which is the first edge in the plank, and basically look at, is the number positive or negative? So is it greater than or less than 0? And separate the geometry based on that. So that's what we have here. These are all the ones that are greater than 0, and these are all the edges that were less than 0 when compared to the first edge in a plank. Once we have that, all of these edges have 2 points, so we can just accumulate a field again, grouped by the island index, which is the same as the edge index. So you could also do just index evaluated on domain of edge would be another way to do that. And so that's going to be, for each edge, 0 at one end and 1 at the other. And so then all we want to do is separate the points now into the index 0 and index 1 ends of the curve, basically. And then we're going to join those together into two groups. So we want if they're pointing in direction A, we take the positive selection from that. And if they are pointing in selection B, we take the negative selection from that and join those together. And that'll be one set of ends. And then we do the opposite for the other, join those together, and that's the other set of ends. And then if we, then we can average the position of all of those and set them all to the same location. So the way we do that is we take the position, we accumulate it, again grouped by the plank, and we count how many points we're evaluating that are in that end cluster. And then we take the average position of those, so the total position of the sum of all of the positions divided by the number of points. And that's the average, so then we set the position of both of these groups to that average position. And then we can join them back together again, turn those vertices into points so that we can turn those points into a curve grouped by our plank ID again, that same value we're using everywhere. And then if we resample the curve so that it only has 2 points, because we currently, at this point, we have all the points are in the same location, but there's 20 points all in that one exact spot. So if we resample it so there's only 2, we eliminate most of those. So now we have a single curve in the place of where each mesh plank goes that's perfectly straight and is approximately aligned to the direction of that plank. So that's actually pretty good. You could stop there if that's all you needed. Or if you want to go a step further, we could now take this curve and increase its resolution and try to fit it to the shape of our input mesh. Because as you can see here, not all of these planks are perfectly straight. And currently our edges don't reach all the way to the end of the curve either. So the way I came up with for doing that was to transfer so first we take our input mesh and we turn it into a bunch of points. And on those points, I capture the island index of the mesh so that that's going to be the same as our plank ID. Our island index on the mesh matches our plank ID that we're using on the curve. So then we can use that to sample from the correct curve to the correct points of the mesh so that we don't run into problems where these are very close together of the curves picking the wrong points. So then first what we're going to do is from the curve on the points, we're going to look at the curve and sample the closest index of a point in the curve. And we're going to use that as an ID to group some accumulate fields to calculate the average position. So I sort of had this here was a good example of this. So, oops, let's turn that off. So here we have our points. We currently have 3 points. We're going to take all of these points here and we're going to find the closest point on the curve, which happens to be this one. And we're going to use that as a group ID in an accumulate field node here to find the center point of that cluster of points that are on the surface of the mesh. And then we're going to sample the closest point here from our curve and transfer this average position back to the curve. And then we're going to move the curve towards that average position. So in this case, this curve would actually be running right here. And then this point right here, the average position of this orange part would be here. So this would get moved that way, if that makes sense. So let's see how we do that with the actual nodes. So right here we've distributed all these points on the faces. Next we need to take our curve and subdivide it so that we add a point in the center. So if this is our curve here, we add a point in the center of it. Then we're going to take that curve and turn it into a mesh. We have to do that because you can't do geometry proximity or sample nearest on a curve. You have to do that on a mesh. Once we have a mesh, we can't sample nearest because it would sample potentially from the wrong curve. It could from a different plank. So since sample nearest doesn't have a group ID, we use geometry proximity and we sample from the group ID of our plank on the curve to the island index ID, which should match, plank 1 is the same as island index 1 in the mesh. To get a position, and then we can sample nearest at the position of the nearest thing. So if the only time it could ever find a different point than the one that geometry proximity found was if you had 2 points in exactly the same place, and in that case we don't care because the position's the same anyway. And so the reason we do that is then from sample nearest we get the index of the point in the curve. So in this curve it might be index 1. And we can use that as a group ID to accumulate for all the points that are closest to that point, so all of these. We can accumulate the position of all of those and find the average position. So that's what we do here. We take the total, we count how many points there are, and then we divide the total sum position of all of the points by the average, or by the number of points to get the average. And then we're going to now sample in the opposite direction. We're going to sample from the closest point back onto the curve that total average. So the way we do that is just the exact opposite of what we did with these nodes here. We do the exact opposite right here. So we're again going to do geometry proximity because we can't do the group ID. But in this case, the group ID is the island index that we saved on the points, and the sample group ID is our planks, so opposite from the first time. And then we're going to sample the nearest at the position, which gets us the index of one of these points on the surface. And then we want to sample at the index of that point the average that's on all of these points. And once we do that, we know where we should move the curve towards. So I just run it through a blur attribute here, excluding the endpoints to smooth it out a little bit. And then we're going to set the position of all of the points to that average of the group of surface points that were placed on the mesh. And then we can just repeat that however many times we want to more accurately match the shape of the curve. So you can see here, this is the original curve with 2 points. If we sample it once, we can get that. Twice, it looks like that. And then 3 times, we start to get the zigzag in there. You can do 4. You go too high, it starts to break. But 4 is a pretty good number. And that is what I came up with. So it's a geometry node. Then I extended the end of it so you can have it go beyond the end, which was useful for me because I wanted to create texture coordinates from it. I'm not going to go into how I did that, but anyway, yeah, that is the node group I came up with. It takes a mesh that has an implied volume, and it tries to run a curve sort of through the center of that. So anyway, like I said, I don't know exactly what all I might use that for yet, but it seems like one of those things that will be a useful generic kind of tool to have in the toolbox to potentially apply to as a solution to different kinds of problems. One of which was this wood grain effect. So for that, you can actually see what we're doing here is, if we do a set position here, you can see I'm actually straightening out all of the beams and placing them so the long axis is aligned to the Z coordinate like this, and then I'm doing those original or the wood grain rings are being applied to that to those coordinates there, but I just don't actually move the mesh there. I just save them as coordinates. So that would be one way to use it, but you could also potentially, like I said, use it for growing like vines around it or wrapping, spiraling something around it. I don't know, it just seems useful to be able to take like a plank kind of mesh or a column or anything that's sort of longer in one direction and fairly straight, and being able to draw a curve through the center of it. Sort of like a reverse deform match curve. It takes the mesh and turns it back into the curve instead of taking the curve and deforming the mesh along it. Anyway, so hopefully you'll find that useful. If you do anything cool with it, let me know. I have a bunch of other tools that I've made for geometry nodes. Most recently, I made one that makes all kinds of rocks. It's called Petrify, but also ropes and strings and generic tools and terrain. So if you're interested in any of that, I'd love to have you check it out. There's info in the description. It's on my website, and they're available for purchase on Superhive now and Gumroad. But other than that, that's all I've got for this one. Thanks for watching.